Thank you. So good morning. First of all, I hope all of you can hear me because I'm kind of concerned that there's no microphone here and there are so many. Plus, you already have to put some extra effort to understand my lovely Italian accent. So two girls, please let me know if the voice is not high enough, and please make me know if you don't understand what I say. So, coming up next on FSN 101, the fats. You now know everything about carbs, and today you enter the realm of lipids, which I can see you're all very excited about. This will not be part of your next exam, which will be on chapter 3 and 4, but of course it will be part of your third exam, so you still have to pay attention. Lipids or fats, first of all, those two names are used, they are equivalent. Someone argues that fats should only refer to lipids that are solid at room temperature, such as butter, whereas the other should be called oil if they're liquid. But in nutrition and in today's lecture and in your book, we use fat as an equivalent name to refer to all kinds of lipid, including the oils. And they are a pretty big class of different molecules with different structures, but they have one thing in common, and that's a physical property, and that's this one. They do not readily dissolve in water. To make life easier, we could say that they are insoluble in water, but well, your book is very precise, so if you really are into it, eventually they will dissolve, but it's not an easy thing. And as you can see in the picture, the experience we all have with oil and vinegar is water-based. You can shake them, they will stay together for 30 seconds, then they will go into two different layers, and because lipids are less dense than water, it will float, and then water-based, like vinegar, will be the bottom layer. And this fact that they do not easily dissolve in water is a heck of a problem in our body, digesting them, absorbing them, and transporting them in our bloodstream, because of course our blood is water-based, and they would float by themselves. So our body has to come up with all kinds of different tricks to digest and transport lipids, as you will see. As I said, there are many different molecules. They're not all of them, but those are the ones that are nutritionally relevant and the one that you will study. Fatty acids are the main building blocks of most lipids on our food and our body. Triglycerides is how most fatty acids are incorporated in a molecule in our body. So 90% of fatty acids, 95 up to 99 in our body of fatty acids are actually incorporated into triglycerides. Phospholipids are quantitatively less important, but still very important in our body because of the functions they have. And then we have sterols, cholesterol, and plant sterols. Those are the two main classes of sterols that you will study. Okay, so what's the most important function of lipids? They have an energetic function. They are very energy dense. 1 gram of lipid has 9 kilocalories. If you remember how many calories is in 1 gram of carbs, how many? 4. So this is more than double what's in carbs or in proteins, because they are so energy dense, and this is also an advantage in storing them because it takes so much less space to store them compared to carbs. Carbs require also a lot of water around them, so we can only store a little bit of them, but the rest, it all goes into lipids. They are the main fuel for our muscle at rest and during light activity. You remember from last week's lecture, carbs are preferentially used as energy source when we do anaerobic activity because we cannot burn fat without oxygen. But when we are at rest, when we do a light activity, actually fats are our main source of energy for our muscle cells. Also, our heart really likes fat. It's the main fuel for fat. But, as again you should already know, there are some organs that cannot use fat for energy, and these are the red blood cells and our brain. They only work with glucose, which is why we will always need some glucose, and which is why our blood glucose needs to be stable and always at some certain level. And again, they are the main form of energy storage in our body, primarily as triglycerides, because they are so energy dense and because they take so less space. Also, you want to remember this fat here. It's not only fat that gets, the fat we eat that gets stored in our body as fat, but also any excess energy. So any excess carbs and any excess proteins that we do not need immediately will just be converted to fat and stored into our adipose tissue. You saw that when we have some extra sugar, some extra glucose, the first thing we do is to store it as not starch, but glycogen. But there's only so much glycogen that we can store. We can have about 200 grams in our liver. Then because it takes so much space, we cannot indefinitely store glycogen. So anything that's left, including carbs, will be converted to fat and stored in our adipose tissues. And there's no limit as to how much fat we can store. So this is again is to see this fat again. Excess carbs and excess proteins will be turned into fat and stored into our adipose tissue. However, once we have made fat, once we have made lipid, there's no way back. Unfortunately, we cannot go back from the fat that we store in our adipose tissue and make glucose, for example, to keep our blood glucose stable. That would be nice, but it doesn't happen. We can take protein. We can do that, sure enough. So you can imagine an arrow that goes from protein to carbs. We can take protein from our muscle and make glucose if needed, if we don't eat enough or if we have a very low carb diet. But there's no way we can do that with fat. So excess carbs and proteins are converted to lipids and stored in the adipose tissue, but there's no way back. Once it's fat, we have to use it as such or keep it. So they are a very important energetic molecule, but that's not their only function. There are actually many more, and we will study this more in details next week. But just to have an idea, they have a very important structural function. Phospholipids and cholesterol are the basic building blocks of the membranes of all cells in our body. So you can see that double layer, that's the cell membrane, all these phospholipids are what makes them, and the yellow little things there is cholesterol. We need both because phospholipids is what makes our cell membranes fluid, and then cholesterol is what makes them more rigid, so it's actually what keeps us in shape. We need a balance, we need both. So they are so very important. Structural components, then, they have a protective function, they have a protective coating on surface of many organs, especially those that are not protected by our bones. For example, think of our kidneys. They are surrounded by a whole layer of perirenal fat that prevents them from being injured, for example, if we fall or if we hit these organs. And the very same function, under our skin, we have a layer of subcutaneous fat that not only protects us when we fall, but it also insulates us. So it helps keeping our internal temperature stable, which is very useful, especially in days like today when it's cold. So I'd better get work on that. And then they also have an important regulatory function. They are precursors of many hormones and hormone-like substances and vitamin D. So they do not only have energetic and structural role, but they also have regulatory functions, so specific molecules that will accomplish some specific function in our body. And again, you will see this more in detail next week. Where are lipids in food? So when we think about lipids, the first idea we have is foods that are primarily sources of lipids, like the pure lipids, butter, oil, mayonnaise. But actually, as you know, lipids are hidden, we could say, in almost all kind of different food. Fruits and vegetables, with some exception, do not have significant amounts of lipids. Then we have some, for example, in milk. Whole milk has 3% of fat, 3.25. Is that a lot? 3% in milk? Why do we make all this noise about low-fat milk, skim, 1%, 2%? Would you say it's a lot? Well, it's not a lot, but you have to think that basically 90% of what's left is water. So if we go and see how much of the energy from milk comes from fat, that's almost half of it. And then because it's a drink, we can drink a lot of it. We can drink one good glass of milk could be 400 ml, so already 12 grams of fat. And because it's not the best type of fat, yes, it's probably better if we don't have too much of it. So that's why we recommend, if we drink a lot of milk, to go for the low-fat version of it. 14% in meat. Now that's after we trim the visible fat, so that steak there probably has a little bit more than 14% because there's some visible fat, but after you trim that away, you're still left with 14% in the actual red part, in the muscle. Cheddar cheese, 33%. Peanuts, 51% in weight of fat, and in general, all nuts and seeds, they are pretty rich sources of fat. Butter, 81%, and again, the rest is water. And then oil, there's no water at all in oil, so 100% of what's in it is lipids, is fat. It's the pure source of fat. And again, this is a picture from your book. It's to say fat is eaten in most foods, even when we recognize some foods as primarily, such this example, primarily carbs, but they're still made with fat. So the only thing you can do to know how much fat is in the food you eat is to check the nutrition facts label and check the serving and check it for hidden fat. So for example, here we have the cheesy proof. I actually brought the very bag where this picture came from. And as you can see there, there's quite a lot of fat. It's 10 grams per serving, one of which is saturated, no fat. So you may think, well, it's quite a lot because 10 grams of fat, how many calories is in it? 90, right? Because it's 9 calories per gram. So times 10, it's 90. That out of the 160, that's the serving, it's more than half. So it's actually quite a lot. But that's one serving. And now, do you know how many servings are in this bag? That's not even a huge one. Take a guess.
7, 11.
10.
Yeah, 11. Let me tell you, 11. And you can tell I'm not a big eater, but if you give me one of those, I'm not going to eat 11 times out of this bag. The label may say it's 11 servings, but my stomach will say that it's 3 or 4 at best. So if you eat, I know somebody that would consider the bag to be 1 serving. Now, if you just eat half of it, then you have to times that 5.5. That makes it 55 grams of lipid. That basically your whole daily allowance of fat, and then some, just by snacking on those. So you could say, well, then let's just go fat-free, low-fat, reduced fat. Now you should already be familiar with the differences between those definitions, and you also have them in the book. I'm not going to go into that, but to have a general idea about this kind of food, the problem with those is that induce eating too much because, sure enough, they have less fat, but the calorie content is usually about the same because if you take fat out and just leave it as that, it will be disgusting. Fat is what gives texture and what gives flavor. The reason we like the cheesy proof is because there's fat. We cannot just take it out and just leave it as that. We have to replace it. Now, we have fat replacers, but they're very expensive. They are not versatile at all. So their use is not very widespread in the industry. Plus, there are some concerns about their use. So what usually happens is that sugar is added in place of fat. So you take fat out, but you put sugar in. And now, is this a good or a bad thing? Well, it can be a very bad thing. Like, take this example here. I don't know if you can see. And I deleted the brand because I have nothing against this one in particular. There's hundreds of products that have exactly the same problem. This is a yogurt, original, Yoo-hoo, 90% fat-free. I can eat a whole lot of it. But then you look at the carbs. And in one serving, in that 1 little serving of yogurt, it's 33 grams, 27 of which simple sugar. Now, 33 grams is huge. To give you an idea, it's 3 full spoons of sugar, not teaspoons, but tablespoons full of sugar in that thing. So that's a horrific amount of sugar. You have to be careful about that as well. You don't want to eat that thing. Just buy your plain yogurt and add your own fruit. And then, just another example, ice grande chai tea latte. Do you want skim milk? Yeah, of course I want skim, but it will be low fat. You know how much sugar? 40 grams. So just to have an idea, sometimes we feel better because we eat low fat, but then it's just killing us from the other side. So it's not that big of an advantage. And this is what happens to the US population. This is you. In the 70s, there was a big study made by a very important leading scientist in the US. His name was Ansel Keys, and he did the so-called 7-country study, went all around the world to see what people would eat and to correlate that with the incidence of obesity and cardiovascular disease. And what he found was that the higher the intake of total fat was correlated with higher incidence of cardiovascular disease. So he concluded that high fat was a bad thing, and because he was such an important scientist, all the nutritional recommendations of the US and the food pyramid and all incorporated this idea that fat is bad. And still today, in the back of the mind of most people, there's this concept that fat is bad. Now, the problem is, he wasn't quite right. That's not the problem. The total amount of fat is not a problem. But because this happened, you start eating less and less fat. This is you going and eating less and less calories from fat. But because that's replaced with sugar, this is you eating more and more sugar. And this is you getting more and more obese. So as you can see, it didn't really help. And there were actually already some indications that this conclusion of this scientist was not quite right. Because, for example, he observed that in the Greek island of Crete, they had a huge consumption of fat. It was more than 40%. So you would predict a high incidence of cardiovascular disease. But actually, the incidence of cardiovascular disease in Greece was the lowest in the world. And the reason for that is that their fat consumption came from mostly olive oil and fish. So it was actually good quality fat. And this brings us to the idea that it doesn't really matter how much fat we eat in general, but what's the quality, what kind of fat. Is it saturated, is it monounsaturated, you will see. And then there was another problem in France. It was very interesting about France because French, they had the very same exact level of fat consumption as the US population, not only the total amount, but also the quality. So they ate the same level of saturated and trans and bad fats, but their incidence of cardiovascular disease, again, was much lower than the US. And you can imagine how much this would bother you. Like, why this French, with all their cheese and dressings and sauces and fat, eating the same bad fat as we do, and they don't die of cardiovascular disease? Well, because someone said, this was called the French paradox, actually, and someone said, it must be because they drink red wine. That's not it, of course. The thing is, they also could eat a whole lot more fruit and vegetables and whole grain cereals and legumes, and this shows that diet in general is still much more important in preventing disease than the specific problem, the specific nutrients, the specific issues. So you can still have a poor fat quality in your diet, but then you can save the day with diet in general. So how much do we need of it? There is not a precise recommendation. The Food and Nutrition Board says you should eat something between 20 and 35% of calories from fat. In general, different agencies, different nutritionists say that anything between 10% and 40% is good, but quality is more important than quantity. So if you eat those 40% all from trans or saturated, then it's bad. However, you also you don't want to eat too much, of course. That would be a risk of overweight because they are so energy dense and we store them in our body, obesity, cardiovascular disease. But also, you don't want to eat too little because of the lack of essential fatty acids. There are some of them, some fatty acids that we cannot really build from carbohydrates, but we need to eat them already preformed as such. That's why they're called essential. They have vital functions in our body. So if you take someone and you just take fat completely out of its diet, and this has been proven on animal studies, eventually the person or the animal will die. You cannot survive if you do not eat fat at all, because you will miss these essential fatty acids, and so you will have problem with immunity, neurological problem, again, cardiovascular risk, and eventually death. Sure.
Well, what's your last mean? Not all fats are great.
Right. We will see this in a moment. Fat is very wide range of different molecules, so they are not equal. There are many different kinds of fatty acids and triglycerides, and we will see this in a moment. So what we really need to know is the differences between them to understand that some of them are good and some of them are not so good.
You mean the function is not sound?
Yeah, not only function, but also them in themselves. They will have differences in the molecule. Sure. Okay, so far so good. So let's go and discover these different types of fats. Fatty acids, as we said before, they are the main building blocks of lipids in food and in our body. But they are not free because they are acidic, so they cannot just go around in our bloodstream as they want. They are incorporated into triglycerides and phospholipids. And the main distinction we have to make is based on their degree of unsaturation. We have saturated fatty acids, SFA, monounsaturated fatty acids, MUFA, and polyunsaturated fatty acids. Okay. Yep, I wait. She was giving me that look like, don't even think about it. Okay. So this is a saturated fatty acid. As you can see, it is a long chain of atoms of carbon. C is for carbon. And each carbon is bound along the chain to two other atoms of carbon, one on his left, one on his right. Chemically, carbons wants to make 4 bonds. So two bonds are made with other atoms of carbon. The remaining 2 bonds are made with hydrogen, H for hydrogen. So it is a long chain of carbons bounded between themselves, and the chain is saturated with atoms of hydrogen. That's why we call it saturated fatty acids, because all the remaining bonds available are filled with this atom of hydrogen. Now, of course, the first carbon of the chain, because it's not bound to another carbon before, it will bind to 3 atoms of carbon, and then on the other side you have a carboxyl group, which is carbon, oxygen, oxygen, hydrogen, and this is the part that actually makes the molecule acidic. So it's the carboxyl end of the fatty acid. If we count the number of carbons, we will count 18. These can vary, so what the difference between the different saturated fatty acids is actually the length of this carbon chain. Down here you have the very same molecule, it's just another way of representing it. Each point here would be a carbon, and the hydrogen are not indicated. So this is a carbon, a carbon, a carbon. If you count, you will count 18. You can also write it like that. C18 means there's 18 atoms of carbon, and the 0, well, you will understand this better when we see the unsaturated, but it means there are no unsaturations. So this is a saturated fatty acid. And it also has its own name. This is called stearic acid with 18 carbons saturated, and it's actually the most important saturated fatty acid in our body. And as you can see, you don't have to write this down. You don't have to know the names, of course, but it's just to indicate that the difference between the different saturated fatty acids is the length of the chain. So some of them will be short chain, some of them longer, some of them even longer. Permitting this is stearic, the one that we saw in the previous slide. You probably also noticed that they all have an even number of carbons. So most naturally occurring fatty acids have an even number of carbons, 4, 6, 12, 14, 16, 18, 20, 22, up to 24. So this is a monounsaturated fatty acid. This is oleic. Again, this has 18 carbons, so just as stearic, but here you see this time those two atoms of carbon, they share two bonds. Now, I'm not sure what's your level of knowledge of chemistry. When we talk about bonds, we actually refer to the electrons that they share. So a single bond would be they share 2 electrons. If we have 2, it means they share double the number of electrons, so 4. But in practice, the consequence of this double bond here between the 2 carbons is that now, see this atom of carbon is already bound 3 times with other carbons, so it doesn't have other 2 bonds available to make with hydrogen, but only 1. So there's 2 less hydrogens in this molecule compared to the stearic acid. Still 18 carbons, but less hydrogen. So this time it's not saturated with hydrogen, and because there is only 1 of these double bonds, it's called monounsaturated. Mono stands for 1. So a single unsaturation. If you count from this end, which is what we call the omega end of the fatty acid, 1, 2, 3, 4, 5, 6, 7, 8, 9. In position 9 from the omega end, we have the double bond. So that's why we say that this fatty acid here, which is called oleic, belongs to the omega-9 family. This means that the first, and only in this case, double bond is 9 carbons away from the omega end. And again, we can write C18 to indicate that's 18 carbons, and 1 in this case means there's 1 unsaturation. You know where it is because it's an omega-9, so it would be 9 carbons away from the omega end. Is that clear? Okay. So another thing I'm sure you notice is that after that bond, the molecule kind of bends. And this is because you have to imagine that the 2 hydrogens are on the same side of the double bond. In this case, we write them as letters, but they are atoms. So because they tend to be on the same side, they kind of push the molecules in this way, and so it will bend. The consequence of this is you cannot, if you have many of these molecules together, you cannot really pile them up as neatly as you would do with a saturated, so they can occupy less space. They are more compact. If you have many unsaturated fatty acids together, it will be a little bit more messy, so it will not be as compact. The consequence of this, so unsaturated fats are less compact than saturated because their chain is bended. The consequence of this is that fats that are rich in saturated fatty acids at room temperature will be solid, so like butter, because their fat is more compact. Whereas fats rich in unsaturated fatty acids, UFA stands for unsaturated, are liquid at room temperature, such as olive oil. Thank you. Now, another thing. We said that, yes, it usually happens that the two hydrogen end up on the same side of the double bond, and this will bend the chain. This is what occurs naturally. So this is what we call the cis form of the fatty acid, meaning that the two hydrogen will be on the same side, so they will push the molecule up, it will bend, and it will be liquid at room temperature and all that. And this is what happens naturally. However, it can also happen that the two hydrogen go on different sides of the double bond, and this is what we call the trans form of the fatty acid. Trans stands for on the other side, so the other side of the molecule, of the double bond. And of course, this time we won't have this problem, so the chain will be linear, and it will behave very similarly as the saturated fat. Because it's linear, it will be again more compact, it will be more solid at room temperature, and when we will see saturated fat has some health issues, well, trans fats, they are unsaturated, but because they behave just as the saturated fat and actually a little bit worse, they are equally as bad, but they are mostly man-made. So they do not occur naturally in food. There's, to some extent, in some kind of food, there are some natural trans fatty acids, such as in milk, but most of them come from human processing of food, such as the process of hydrogenation of fats, which we will see later. So cis form, double bond and bound molecule, naturally occurring, and then the trans form is linear, and it's mostly man-made. And now we go to the polyunsaturated fat, as you can easily imagine at this point. This time we have double bonds, but we do not have one, we have two or more, and in this case we will refer to this fatty acid as the polyunsaturated. This molecule here is linoleic acid. It's very important. It's one of the two essential fatty acids in our diet. It has two double bonds, and if we count from the omega end, 1, 2, 3, 4, 5, 6, the first is in position 6, so it belongs to the omega-6 family. The other important nutritionally relevant family of polyunsaturated is this one, omega-3. Alpha-linolenic is the essential omega-3, so those are the two essential fatty acids in our diet, linoleic omega-6 and alpha-linolenic omega-3. And again, of course, omega-3, because if we count from the omega end, 1, 2, 3 carbons, we have the first double bond. C18, again, it means that it has 18 carbons. 3, it's for 3 double bonds. Omega-3, because the first double bond is 3 carbons away from the omega end. We make all our examples with 18 carbons. Now, again, the length of the chain can vary, but 18 is kind of the favorite number. In our body, most of fatty acids incorporated in triglycerides will be this long, 18 atoms of carbon. And this is also the reason why the two essential fatty acids, linoleic and linolenic, are 18 carbons long. Now, why do we have to make these distinctions, saturated, monounsaturated, poly, omega-6, omega-3? Well, we need to see kind of what they do in our body and where we find them in food. Saturated fatty acids, they are mainly, but not exclusively, found in food of animal origin. They are nutritionally non-essential. I'm sure you already are familiar with the concept of nutrition essentiality. It doesn't mean that they are not important. They are still vital. They perform very important functions in our body. But when we say that they are nutritionally non-essential, we just mean that our body can build them from other molecules. Such, for example, carbs. There's no sugar that's essential. That they are all non-essential. That doesn't mean they're not important. But it means that our body can make sugar from, for example, protein. And saturated fatty acid, we saw before, can be made, for example, by carbs or by proteins. Again, they can be converted into one another. So we don't really need to eat them as such. Our body can build them if it needs them. So that's why we say non-essential. But they're still very important. However, an excess of saturated fatty acids in our diet is detrimental, and this is kind of, I think, common knowledge nowadays, because many of them are atherogenic. By atherogenic, we mean they tend to deposit into the wall of our arteries and therefore promoting atherosclerosis and putting us at risk for cardiovascular disease. So we don't want too many of them. And that's why you will see, when you will see the recommendations for the intake of fats, that actually there is a limit of about 10% energy from saturated fat that should come from our diet. We don't want too many. However, another concept that you may want to keep in mind, and this is, I'm not sure this is in your book, but well, just I'll tell you so. Not all saturated fatty acids are all equally atherogenic, so it's not necessarily true that all saturated fat is bad. And please do not write this down. It's just to confirm this concept. Some saturated fats are actually innocent, such as stearic. It gets easily converted into oleic, so it's not a big problem for our body. There are others that are kind of neutral, but then there are others that are real bad. So those are really atherogenic and they have a high risk for cardiovascular disease, such as the two guys here in the middle. This slide shows, well, first the concept that the most important sources of saturated fat in our diet is animal food, eggs, meat, milk, dairy, but not exclusively. As you see there on the end, there's also some vegetable sources of saturated fat. There's coconut and palm. It's not that we eat it as such usually, but it's two products, two fruits that are used a lot by the food industry to take out oils to be used in food processing. So coconut kernel oil, palm oil, and palm oil is what we make from the pulp of the palm, the yellow, and then palm kernel oil is what we make from this yellow kernel. They are very rich in saturated fat, and not only that, but as you can see here, the little smiley faces, it's actually the worst kind of saturated fat. So those two bad guys that were in the middle in the previous slide, they were the ones that are mostly atherogenic. Well, coconut kernel and palm kernel oil are very rich in those bad fats. So we don't want to have these tropical fats in the food, and we want to check the ingredients list of the food we buy to make sure there's not too much of them. And yes, this arrow kind of tells you again that even if some animal foods are rich in saturated fat, but for example eggs, they have a lot of stearic, so it's not so bad. And then as you move toward the right, it's more of the palmitic, and then the lauric and the myristic, so the worst type of saturated fat. Monounsaturated, omega-9, it's the nutritionally relevant family. You recognize oleic that we saw before. There are other, and again you see the differences is because they have different length of the chain. Again, they are not nutritionally essential because they can be built from the corresponding saturated fatty acid of the same length. So for example, stearic, that's 18 carbon long, can be converted into oleic because our body can introduce the double bond in position 9. So it's non-essential, but still very important because oleic acid is probably the best possible fatty acid in our diet. It is highly beneficial for health. It lowers blood cholesterol. It will do all sorts of good things, and again, you will learn them next week. Now, forget this thing about the rusic because it's not in your book. It's just it was once present in rapeseed oil. That's why it couldn't be sold for a lot of time. but now they have developed a genetically modified version of rapeseed oil. They changed their name because it was not nice, because everybody knew about the erucic, so it's called canola oil, but that's rich in oleic acid, so that's good. We don't have this problem anymore. Where do we find the good oleic acid? Well, olive oil and, of course, olives, where olive oil comes from. And this should really be our main source of oleic acid in the diet. It's a good oil. It does not easily get oxidized, so it doesn't have a lot of problem storing it. But also, we have a lot of oleic acid in the macadamia nuts. If any one of you has ever been on the Atkins diet, I'm sure you're familiar with macadamia nuts, avocado, canola oil, again, and peanuts. About half the fat in peanuts is polyunsaturated, but the other half is oleic acid. The polyunsaturated of the omega-6 family, this time we have linoleic acid, the one you have on top, C18 with 2 double bonds. You don't need to remember the structure. You will never be asked how many double bonds or to draw the picture of the fatty acid. But this is a omega-6 and it is essential. Again, this is because there's no way that our body can make linoleic acid starting from other fatty acids or from other nutrients. We have to find it in the diet. We have to find it in food, and we better find it because it's very important. It makes a lot of essential functions, and then it's precursor of some hormone-like substances that regulate blood pressure and immunity and inflammation, so we need it. All the other omega-6 with different chain length can be derived from linoleic. So once we have the linoleic, we can build all the other omega-6 we need, and we don't have to worry about finding them in the diet. However, this is not a big problem, luckily, because linoleic acid is pretty common in food. We find it in most vegetable and animal food. However, the richest sources of it are nuts and seeds in general, and the oil that we make from them. So corn oil, sunflower oil, those are rich in omega-6 linoleic. The polyunsaturated fatty acids of the omega-3 family. Again, you notice you don't have to know the names, but they're different. They have more than 2 double bonds. The first one is always in position 3 from the omega end, and they have different length of the chain. The one on top, alpha-linolenic acid, is essential, is the other essential. So there's 2 essential fatty acids in our diet. One is omega-6 linoleic, the other is omega-3 alpha-linolenic. All the other omega-3, again, can be derived, so our body can build them starting from alpha-linolenic. However, this time there's kind of a different problem. The first one is that alpha-linolenic is not as widespread in food as linoleic is, so it could be more tough to find in our diet. And the other problem is that the conversion of this fatty acid into the other 2 that are still important, although not strictly essential, is very slow. And this is the reason why most nutritionists recommend having a direct intake of those 2 fatty acids. I'm not even pronouncing the names. Eicosapentaenoic and docosahexaenoic, EPA and DHA. Those are mainly found, as we will see, in fish, omega-3 of fish. It's still advisable to have a direct intake of them. They're not strictly essential because we can make them if we have alpha-linolenic, but it's low and we don't have a lot of alpha-linolenic in the first place, so it's advisable to find them directly in food. Alpha-linolenic we find in flax seeds. They're the most important source of it, and flaxseed oil. But it's not a good idea to keep flaxseed oil because it gets very easily oxidized, so rancidity is a problem because it's highly unsaturated. Once it gets rancid, it's actually dangerous. We will see that. And walnuts. Portulaca, I don't think, we don't eat it in Europe. I don't think you eat it here as well. But it's what you give to some animals to make, for example, to have eggs enriched in omega-3, then you feed the animal this source of omega-3 so that they will be present in the food. EPA and DHA, the other two, not strictly essential but still advisable omega-3. They are found in fish, fatty fish. Now, when we talk about fish, being fat is not a problem because the fat in fish is actually a good one. So we are not worried about that. Actually, we like it. So if a fish is rich in fat, that's a good thing. Salmon, anchovy, sardine, and also the lobster I put there because it's a rich source since we are in Maine. Eating at least 2 to 3 servings of fish per week will provide us all the EPA and DHA that we need. We can also find, as I was mentioning before, some in omega-3 enriched foods, such as eggs, some seaweeds, but we cannot really know how much is in it, and fish oil supplements. So if somebody is vegetarian or vegan, how many vegetarians and vegans? No. A few years ago, half the room would have been vegetarian. Well, that's not a problem. You just want to make sure that you eat enough walnuts and flax seeds to have your omega-3. Now, this is another thing that you don't need to write down what will be in this slide, but to give an idea, why do we have to make this distinction? Why are we making this noise about omega-3, omega-6? Well, because they are actually have different functions in our body. And the functions they have are kind of opposite. So from these molecules, we build some hormone-like substances that are called eicosanoids, that they are very important in our metabolism. And the way I picture this is sort of this pulling rope game, where there's omega-6 team on one side, omega-3 on the other. And so let's see just the first example to have an idea. Omega-3, they promote blood fluidity. So if the omega-3 teams would win, that wouldn't be good because it would mean that the very first little cut in our finger, we would bleed to death because we cannot heal the wound. But on the other hand, omega-6, that do exactly the opposite. They promote platelet aggregation. We don't want them to win either because then we will have blood clots in our bloodstream with high risk of heart attack and stroke. So what we want is a little bit of both and have a balance. That's why we need both of them in the diet in appropriate amounts. And the same goes for all other effects on blood pressure and immune system and inflammation. So the key is balance. What we want is a good ratio of omega-3 versus omega-6. Per every part of omega-3, we want 2 to 4 the amount of omega-6. So for example, for every gram of omega-3, we want 2 to 4 grams of omega-6, and that will give us the right balance to have a good health situation as far as those effects go. The other problems with polyunsaturated fatty acids is oxidation. The more unsaturations we have in a fatty acids, the easier it gets oxidized. When it gets oxidized and rancid, well, if a fat goes rancid, it's not a big problem because we can smell it and we usually don't eat it. But the thing is, it can get oxidized before it actually smells bad or looks spoiled, so we can still eat it. But that's bad because it's highly carcinogenic and atherogenic molecules, toxic products. So what was good, our omega-3 and omega-6, and we need that becomes bad. And that happens, and did you remember the slide where there was flaxseed oil and I wrote rancid? Because that's very highly unsaturated, so it's very likely that if we store it badly, it will oxidize. That happens with bad storage. If it's exposed for a long time to light, air, oxygen, heat, and also because this happens with heat, when we have high temperature cooking of unsaturated fats, such as deep frying, you will always generate some of these oxidized toxic lipids that at this point they don't do any good. So what we want to do is to prevent fat rancidity. The food industry does that by adding fat-soluble antioxidants such as vitamin E or the artificial one, BHA, BHT. They will oxidize themselves and therefore kind of spare the fat from oxidizing, but they can only do it for the shelf life of the product. Then once vitamin E and BHA and BHT are fully oxidized themselves, then you will start having oxidation of your fats. And this is the same thing that happens in oils. Oil naturally comes with some vitamin E, and that will save them from getting oxidized for a certain amount of time. Then once vitamin E is over, then you will start having oxidations on the fatty acids of your oil. At home, we want to store oils and nuts in a dry and cool place, protect from light, or if we cannot find such a place, it's better to keep them in the fridge. Of course, get rid of rancid or badly stored oils, and limit consumption of deep-fried food, because we know that the fat inevitably gets degraded and form those toxic compounds. Hydrogenation, this is the other issue. So there is this common widespread idea, because animal food is rich in saturated fat that's not so good, and vegetable oils are rich in unsaturated fat that's good. The consumers have this conception, so they had in the past this idea that it was better to eat less butter and more oil. But the problem with that is that they are not exactly the same, and the main difference is because butter is rich in saturated fat and solid at room temperature. You can spread it on bread. You cannot do that with an oil. But some smart guy in the food industry at some point with knowledge of chemistry said, you know what we can do? We can take the vegetable oil with its unsaturated fats and artificially saturated, hydrogenated it. If we bubble hydrogen at high pressure into our unsaturated vegetable oil that's liquid, then we fill all those double bonds with hydrogen and it will become solid, semi-solid. That's margarine. But, so, it is a process used to solidify an oil, addition of hydrogen to the double bonds to convert unsaturated fat into saturated, and so what you will end up with is a product that is still made from vegetable oil, but is semi-solid or solid at room temperature, so you can use it as butter. But as you can easily imagine, and even a first grader can understand that, if the good thing about vegetable oil is that it's liquid precisely because it has unsaturated fats that are the good ones. If we take them and make them saturated, then they will behave just the same as a saturated fat from animal food. It's not that our body will make the difference when it says a saturated fat and says, oh, look, that's saturated, but it comes from vegetable oil, so it must be good. It doesn't happen. It's saturated and it behaves just the same. It will have just the same problems on our health. But then the other problem is that because of how this process happens, what happens is you take the unsaturated fat, such as oleic, that is banned, you have this intermediate product, which is the transform. So you take the hydrogen, they go on different sides of the double bond, the chains become linear, and then you saturate that bond with hydrogen, and it becomes saturated, so solid. The thing is, when you do the hydrogenation, you don't do it fully, because then you will end up with a product that it's very solid. You use it as a hammer, but you cannot spread it on bread. So what you usually do is a partial hydrogenation. Partial hydrogenation, it will be different degrees of this process. You stop at some point. So you will still have some unsaturated, some saturated, and also a lot of these intermediate products, that's the trans. fatty acid. Now the problem with trans is that not only it's linear, so it behaves in our body as a saturated fat, but because it has that strange bond with the hydrogen on different sides that our body is not really familiar with, it doesn't really know what to do with it. It has a hard time incorporating into triglycerides, putting in the adipose tissue. So most of the times what happens is that it will just stay in our bloodstream and then up in the walls of our arteries, and therefore they are highly atherogenic, even more than saturated fat themselves. So trans fatty acids are highly atherogenic, even more than saturated fats. They are mostly man-made, found in food containing hydrogenated and especially partially hydrogenated fats, stick margarines and shortenings, deep fried food, and again, if they are fried into a partially hydrogenated fat, which is usually the case, high-fat baked goods or non-dairy creamers, again, because they are made with partially hydrogenated fat. Now, when you buy your food at the store, you can check the label and make sure there's not a lot of trans fats. Now, you know when you have the 0 in the back, it doesn't mean it's really 0, right? It's less than 0.5. So there could still be some. You may want to check the ingredients. If you find partially hydrogenated fats, it's probably mean there's some trans, unless there's a specific claim on top that says 0 trans fat or trans fat free. That really means that should be minimal amounts of trans fats. And still we can eat some. It's not that they are bad inherently. They're bad if we have too many of them. Okay. So any questions so far before we go into the triglycerides? Yeah.
I was wondering if margarine is better to use or butter.
I'm sorry?
Which one is better to consume, like in bigger quantities?
Well, today you want to check the label. Nowadays we have technologies to make margarine with limited amount of trans fats. So if that's labeled as trans-free or low in trans fats, it's probably better to use margarine. But you shouldn't eat too much of both, so you can also eat butter. It's not that they are inherently evil. Okay, so as we said, this should all be a repetition. About 95% of fatty acids in food, and even more, probably 99% of fatty acids in the human body are not free because they are acidic, but they are incorporated into triglycerides. And triglycerides are the main form of energy storage in our body. So the way we store fat in our adipose tissue is we put the fatty acids into the triglycerides and store them. How is a triglyceride made? Okay, so you should recognize here we have our 3 fatty acids. In this case, there are 3 molecules of stearic, but they don't have to be the same. They can be 3 different fatty acids. They can have different length of the chain or different degrees of unsaturation, although, again, the preferential way of storing fat in our adipose tissue is using the 18-carbon stearic acid. And here, there's a molecule. You should be kind of familiar with this structure. It is a sugar with 3 carbons. It's called glycerol. So what happens is that you will have a condensation reaction whereby you take a molecule of water out, and you will have a bond between this oxygen in the carboxyl end of the fatty acid and the carbon, each of the 3 carbons of the glycerol molecule of water goes out, and you will have your bond between oxygen and carbon. So in this way, you kind of take your 3 fatty acids and clamp them together, keep them together by means of this molecule of glycerol. The phospholipid, it is similar. You see this one here, again, is a molecule of glycerol, but this time it only binds 2 fatty acids. It could also be just 1, but it's generally 2 fatty acids, and then the remaining carbon is bound to a phosphorus-containing compounds and then something else. What really characterizes the phospholipid is that there is this phosphorus here. That's why we call it phospholipid, and that gives specific properties to this molecule, which is why they are so very important in our body. This specific phospholipid is lecithin, and it's the most abundant phospholipid in food. Their nutrition is non-essential. Again, they are important, very important, but non-essential because we can make them. They are abundant in this food with germ peanuts, egg yolk, soybeans, organ meat. But again, it's not so important because we can make them ourselves when we need them. Their most important function is that they are components of the cell membranes. You remember that double layer that surrounds all of our cells. It's made primarily of phospholipids. And also, their very important property is that they act as emulsifiers in our body. And this is what actually makes digestion and transport of fats possible. And also in food industry, emulsifiers means that they prevent the separation of lipid and water mixtures. So if we shake our oil and vinegar and that's it, they will separate. If we shake them and add a phospholipid such as lecithin as an emulsifier, then they will not separate anymore. So the mixture will stay. So for example, if you want to make a salad dressing, you will need an emulsifier such as lecithin. The reason why they act as emulsifier, again, we have the same molecule we saw before, is that because of the presence of these phosphorus compounds, they are not really complying with the rule that lipids are insoluble in water. Phospholipids are actually partially soluble because the tail where you have the fatty acids, it will be hydrophobic, meaning it doesn't like water. It's insoluble because it's non-polar. But this other end with the phosphorus is actually polar, so hydrophilic. It likes water. It can face water and be fine with it. So many times the way phospholipids are depicted in drawings is kind of like that, where you have the polar head on one hand that likes water, and then you have the tail that's hydrophobic, it doesn't like water but likes fat, and those two tails would be the two fatty acids which the glycerols bound. This means that if this would represent like a water layer, this would represent a fat layer. If we add our phospholipid, they will place themselves in space in a way that they will have all the polar heads that likes water towards the water layer, and then all the hydrophobic tails that don't like water but like fat towards the adipose layer. And that's what happens, for example, in the membranes of our cells. That's our membrane. This would be, for example, the inside of the cell. The cytoplasm is water-based. The outside, the bloodstream or the interstitial space is water. But then you have those two layers of phospholipids facing outside with their polar heads, the water compartments, and then creating this hydrophobic barrier that's actually what's constituted the membrane, so that molecules cannot just go in and out of the cell the way they want, but this can be strictly regulated because they will kind of bounce back when finding this barrier of hydrophobic layer. And this is another thing that will always happen if you throw a bunch of phospholipids in water. They will just form this sphere that's called a micelle with all the polar heads outside and all the hydrophobic tails inside. And this is the way that, for example, lipids are transported in our bloodstream. So we will have all of our fat and cholesterol that we need to transport in our blood in the center of this structure. And this can go into the bloodstream because on the outside you have all the polar heads that go along, that get along with blood that's water-based. So this will be called a lipoprotein, as you will see next week. And this again, you have it in your book. It shows how if you add a lecithin or a phospholipid into your mixture of water and oil, you shake it, and then this time it won't separate anymore because you will have this micelle keeping the little droplets of fat as such without separation. Finally, there's cholesterol. As you can see now, we have a very different molecule. This is completely different. There's no fatty acid, but still, because it does not readily dissolve in water, it is a lipid. Cholesterol is it's not a poison, it's not a disease, it's actually very important in our body, it performs all kinds of important functions. It is only found in animal food, so this is a typical animal fat. You will not find cholesterol in vegetable sources. This is a typical exam question, hint, hint, hint. You usually have a list of foods and ask which one of these food has less cholesterol. And then you have some food that look lean, like chicken breast or 1% milk, but they are animal. And then you have some fat vegetable like peanut butter, and you will say, geez, it must have a lot of cholesterol. And if you don't know that, it cannot be because you will never find cholesterol in oil or peanut butter because it's fat, but it's vegetable. So there's no way you can have cholesterol. Whereas chicken breast, skim milk, they will not have a lot of fat and not a lot of cholesterol, but there will be some because it's an animal source of fat. Yes?
Do you find it in the vegetable oils?
No? Unless it's added, there will not be cholesterol in vegetable oil. As we said, it's an important molecule. We already mentioned that it's a component of cell membranes. It what gives them structure, rigidity, it what keeps us in shape. It's a precursor of bile salts. It's what bile salts that we need to emulsify lipids during fat digestion. You will see this more in detail next week. It's a precursor of vitamin D. We can eat vitamin D in food, but we can also make vitamin D ourselves in the skin if we are exposed to light. But in order to do that, we need to have cholesterol to start building it. And then it's a precursor of some hormones, such as androgen, estrogens. So it's very important. Where we do not want cholesterol too much is in our bloodstream, because if we have too much cholesterol, it doesn't get into the cell, then yes, it will end up depositing into the wall of our arteries and be atherogenic, cause cardiovascular disease. But once it gets inside the cell, it's actually very important and vital. The plant sterols, this is the last slide. They are sterols like cholesterol, but the structure is different. We cannot absorb them, so they are not nutritionally strictly relevant because we will eat them and not be able to absorb them. But they still have an important, potentially important function in our diet because they interfere with the absorption of cholesterol in our gastrointestinal tract. So if someone has problem with high blood cholesterol, actually a moderate intake of about 2 grams of plant sterols every day, it will help lowering blood cholesterol because it will interfere with absorption of cholesterol from food and especially from bile salts, because recycling bile salts is the way cholesterol is recycled in our body. If we prevent that, then we will lose it, and therefore our blood cholesterol will decrease. That's it. If you have any questions, yes?
Are phospholipids are multipliers? Are phospholipids the only multipliers, or are there other multipliers?
No, there are others.